Good afternoon, students. So I will start the class. So here in the last class, in the previous classes, we have studied the basic information regarding of the first unit. That is your mathematical concept of different coordinate system. In that case, we have seen the three different coordinate systems also. And your gradient topic, Laplace transformation, then curl divergence, all these things that we have studied. That was the part of our module 1 that has been completed. Now in the previous class I have told you the module 2. In the last class the module 2 has been started, and we have done some basic information related your electrostatics path. This one has been cleared. This one concept has been cleared in the last class. Principle of superposition had been already cleared in the previous class, in which many number of terms are many no, sorry many charges, multiple charges are present, and you have to calculate the force at a particular for a particular charge acting on a acting force on that charge due to other multiple charges. In that case the formula is this one. The electric field intensity that is related with your that is the definition of electric field intensity related with this F force exerted on the multiple charges, you can derive from this one also. That is force per unit charge can be rectified as your electric field intensity. So definition of electric field intensity, it is written, it is the force per unit charge when placed in the electric field. Okay, now it can be written as E equal to F by Q. Unit is Newton per coulomb or volt per meter. Okay, either of them can be used as the unit of electric field intensity, whether either you can use Newton per coulomb or volt per meter. Okay, now accordingly, if you want to write the equation of your electric field intensity, then this will be equation for your charges, and this is the vector in terms of vector notification. This electric field intensity is been written, the unit has been taken as Newton per coulomb. In general you can write E equal to Q, or you can say in general, or you can say with the notation of the unit vector, we can write the electric field intensity in this format: E equal to Q unit vector AR in the radial direction, then 4 pi epsilon naught R square. Okay, now accordingly, if you have multiple charges, then you can write the electric field intensity using this formula. Okay, that we have discussed in the previous classes. Then we have seen the how we can relate the continuous charge distribution, how it been represented, the total charge present to electric field intensity, the total charge due to the line charge, surface charge, and volume charge is represented by this formula. Then we have discussed the electric field intensity in terms of a line charge, surface charge, and volume charge in the volume charge density. So accordingly the formula can be implemented to find the value of electric field intensity depending upon the application, whether it is line charge or surface charge or volume charge density. Now we were discussing about the electric field intensity due to line charge. Let us take the line charge that we have taken, that is from A to B. That is from A to B as a line charge in which positive charges are placed or positive charges are induced. Okay, now first according to this diagram, let me introduce the theoretical concept here. Here we have taken, let us consider a line charge along the z-axis spread from A to B and having line charge density rho L. Okay, let us consider small length dl along AB having charge element dl at z dash. Okay, it doesn't have any x or y coordinate, only z dash is, or z coordinate is there. Okay, so we have taken AB as a line charge where positive charges are induced and having the line charge density as rho L. Now let us suppose a particular element. Let us suppose due to this line charge, we have to find the electric field intensity at this point. Let us say this is point P whose coordinate is x, y, z. Now we have to find your electric field intensity at this point due to this line charge A to B. For that, let us proceed how we can calculate the electric field intensity at point P due to this line charge AB. As we have discussed, this AB is a line charge having density rho L, and this P is at a particular distance, at a position vector at a particular distance away from this line charge AL. Now from point P, let us draw a straight line to point P, making first from point P. Let us draw a perpendicular on the z-axis. On the z-axis, we have this is perpendicular from the point P. As you know, the radial distance from the z-axis to a point P is called your radial distance. Is called radial distance. So it is represented as your rho. That's why it is represented as rho. Now draw a line from point P to B, making angle alpha 2 with the perpendicular line. Similar, connect the point A with the point B, which makes an angle alpha 1 with the perpendicular one. And let us consider a small elemental length dl along the AB, whose coordinate is 0 0 z dash, as this is along the z axis, so it doesn't have any x or y coordinate parameter. Only z parameter will be there, and it is named as z dash. That means this dl has coordinate 0 0 z dash. Now this AB is of a very small very small length we have considered. Let us say this is having length L. Okay. Now out of this, if you have the value of dl, and when you integrate from A to B, you will get all the total line length of this AB. Okay, this point P, this point T, that is the point T is perpendicular from point P on the z axis. So let us consider this is at the your z axis, on the z axis. So it is represented at 0 0 z. This is the coordinate or parameter of the point T on the z axis. That is having value, any value of it can be of any value. If we want to replace z as 10 meter or 20 meter, whatever with the value, this will lies on the z axis. So the point T has coordinate 0 0 z, P has coordinate x y z, and this dl has length, has coordinate 0 0 z dash. This is, as this dl is along the z axis, so we can write this dl at dz also, as this is as this dl has the coordinate 0 0 z dash. So we can write that dl equal to dz also, z dash also. Okay. Mm, So from there you will get dl equal to dz. Now what will the total line charge? In the previous class we have studied for the line charge. This is the formula, that is total charge along the line AB. Here the total charge along the line AB is integration over the length rho L dl. So integration over the length, that is range from A to B, will lies rho L dl. Here we have taken the particular length, that if we have the finite value of the length, then we can put the value of that finite length. This, the lower range is A, and that means length is varies from A to B, or you can say the angle varies from alpha 1 to alpha 2. Okay, as point A makes an angle alpha 1 with the perpendicular, and point B makes an angle alpha 2 with the perpendicular. So we can write A to B line length rho L dl. A to B, this dl is represented in terms of dz dash. So this dl is replaced by first dz and then dz dash. Now we have to find some parameters from this diagram, so that we can derive the electric field intensity due to this line charge. Okay. Now for that value, AB rho L dz has been has been obtained for the total charge value, total charge Q of the value AB line length. Now from the figure you can say this dl making an angle alpha, as this dl is connected with the point P with the position vector capital R vector R, and this line capital R position vector making an angle alpha with the perpendicular. Now for this value cos alpha, when you write, this is your base term, and this is your perpendicular term, and this is the hypotenuse. That means cos alpha will be rho upon R. This will be rho upon R. Here we have taken the magnitude term. So from there you will get R equal to rho upon cos alpha, and 1 upon cos alpha is sec alpha. That's why R equal to rho sec alpha we have taken. Now tan alpha means this is the angle. Tan alpha means as this angle alpha making an angle with the dl and the point P. So the tan alpha will be base, perpendicular upon base. The perpendicular point lies from dl to this point T, as this is the triangle, so for tan alpha you have the value as the upper tip of the perpendicular is dl, the lower tip is point t, and the base is connected this point t with the p. That means this coordinate up to this distance, as we know from the coordinate system, or you can say algebra mathematical expression, we know the value of x parameters does not lie, y is 0, then the distance between this t and dl will be z minus z dash, z minus z dash dz. That is the value, z minus z dash divided by rho, that is z minus z dash upon rho. So from there you will get z minus z dash equal to rho tan alpha. Accordingly, if you write the value r equal to, as you can say, you have the value of, this is the r value, this is the position vector. So position vector for the z axis, as you moving from z dash to z, okay, and then z t to p. So this position vector r can be written as, first you have to move, the distance is z minus z dash in the z direction, or you can say in the z axis. So it is written as z minus z dash az in the, this is represent the direction of the movement. So the value z minus z dash will move along the z axis, so it is represented as az, plus we are moving along the positive y axis, so it will represented by positive sign, as we are moving from t to point p. So the value will be rho arrow cap, that is rho arrow cap with the positive sign. So the total the value of the position vector, capital R vector, is this z minus z dash az plus rho arrow. Now, as we know, the value of the electric field intensity for the line charge, this is the formula, that is value of the electric field intensity due to line charge is the line length over integration over the length rho l dl 4 pi epsilon naught r square ar. This is the magnitude. If you want to write the in direction form, then this will be ar will be represented in terms of the vector divided by its magnitude. That means it will become rq, and the vector r will be in the numerator part. So from here you can say the electric field intensity formula is integration over the length rho l dl 4 pi epsilon naught r square ar. Now E equal to over the length L rho l dl. This ar unit vector ar is represented in terms of vector form, so it is represented as vector r divided by magnitude of r. That will, when you multiply with r square, it will become rq. So accordingly, rho l r dl divided by 4 pi epsilon naught rq will be there. Then again, as this dl is represented by dz dash, this dl is represented by dz dash, so it will be replaced, this dl will be replaced with dz dash. So up to this, there is no confusion. The electric field intensity is equal to the integration over the length rho l vector r dz dash divided by 4 pi epsilon naught rq. Now in the next page, you can see that integration over the length, that is the integration over the length rho l is placed. Then vector r has some value here. We have derived some position vector value of the position vector r. So put that value vector r here. So we have put it the value z minus z dash az plus rho arrow, and tz dash is placed as it is. So dz dash is placed as 4 pi epsilon naught. 4 pi epsilon naught, put the value of rq in magnitude term. So accordingly, we have put it the value z minus z dash square plus rho square up to the power 3 by 2. So this is not very much tough. This is mathematical calculation. Now put the value of z minus z dash, as you have derived z minus z dash equal to rho tan alpha. So z minus z dash will be, as you know, rho arrow cap plus z minus z dash is rho tan alpha, and this az is placed as it is. Then dz dash, then in the denominator part 4 by epsilon naught z minus z dash ka whole square. That means rho square tan square alpha plus rho square will be there. Take out rho square is common in this denominator part, so take out the rho square, it will become 1 plus tan square alpha. In the upper part, when you take out the rho value from the bracket, you will get arrow cap plus tan alpha az. Just simplify this format, you will get the as you know, this row and this row will be cancelled, as this is square term and this is single term, so it will be cancelled as in the denominator part there will be only row will be there. So accordingly, if you solve this equation, that is rho l dot rho arrow cap plus tan alpha az dz dash divided by 4 pi epsilon naught rho square, when you multiply you will get rho cube. That means square into 3 divided by 2. So 2 will be cancelled, only rho q will be there. So accordingly, if you solve this if you solve this equation, you will get final term this integration format, that is integration over the length rho l into rho a rho cap plus tan alpha az dz dash divided by 4 pi epsilon naught rho q sec q alpha. Okay, as we know, in this format we have derived z minus dz dash equal to rho tan alpha. So here we can see that the integration over the length is with respect to dz dash we are deriving. So here we can say that you can see that z minus z dash equal to rho tan alpha. If you differentiate this whole equation with respect to dz dash, you will get the in terms of dz dash, that means this is your constant value, z is your constant value. So minus dz dash equal to tan alpha have the derivative sec square alpha. Now this dz dash is related with your alpha, so the length or the integration over the length will be the range will vary it from, now it will be converted into alpha angle. Now you can put rho integration over the length rho l into rho a rho cap plus tan alpha az cap, and put the value of dz dash from this equation, that is minus rho sec square alpha d alpha minus rho sec square alpha d alpha 4 pi epsilon naught rho q sec q. Denominator is placed as it is. Now just cancel some terms from the numerator and denominator part, you will get this equation. This line will you will get for the electric field intensity. Now here you can say integration over the length minus rho l aero cap plus tan alpha az cap d alpha 4 pi epsilon naught rho sec alpha. Now this whole integration is integrated with respect to now alpha. As we know, the integration from this diagram, you can say this point P making an angle of, that means AB line length is varies from alpha 1 to alpha 2. So we can put the line length or the range from alpha 1 to alpha 2. Alpha 1 to alpha 2 we can put. Now first we have to take out the constant term. Here you can say minus rho l upon 4 pi epsilon naught is constant, so we have taken out the this constant term from the integration part. Now the remaining part is left, that is integration over the length aero cap plus tan alpha az cap d alpha upon sec alpha. Now bifurcate this total equation with respect to the LCM, you will get 1 upon sec alpha aero cap plus tan alpha upon sec alpha az cap d alpha. Okay, now again if you as the range is vary from point A varies from point A to B varies from alpha 1 to alpha 2, and this integration varies in terms of alpha, so we have take the range from alpha 1 to alpha 2. 1 upon sec alpha become cos alpha, so we have put it the value of cos alpha. Now when you solve this tan alpha upon sec alpha, you will get sin alpha. So this will be sin alpha and the direction will remain as it is. Now this is the constant term. When you integrate this cos alpha, you will get sin alpha, and the range will rise from alpha 1 to alpha 2, but the direction of the movement will not change. That is aero cap will be there. Here sin alpha integration, you will get minus cos alpha range from alpha 1 to alpha 2, but the direction of movement that will remain constant, that is in the z direction. Now here you can see that minus rho l upon 4 pi epsilon naught upon 4 pi epsilon naught. When you solve this equation, sin alpha 2 minus sin alpha 1, that is a aero cap minus, as this plus minus become minus, cos alpha 2 minus cos alpha 1 in the z direction. When you solve this equation, or when you place accordingly, this minus term will be taken within the parenthesis or within the bracket. You will get this electric field intensity formula for a line charge, that is rho l upon 4 pi epsilon naught rho, that is cos alpha 2. This will become minus value become positive, and this positive will become negative. So accordingly, if you put the value, you will get E equal to rho l 4 pi epsilon naught rho cos alpha 2 minus cos alpha 1 az cap minus sin alpha 2 minus sin alpha 1 aero cap. So this is the actual electric field intensity formula for your line charge. Okay, so this is the electric field intensity formula for your line charge. Now there are some conditions based on this formula. That means case one, you can see for infinite line charge. Let us say this charge is of infinite length. If this have infinite length, that means b point will be somewhat in the infinite position. So accordingly, if you place, then alpha 1 will be 90 degree. That means this alpha 1 will be your 90 degree. Then let us say this will be your b as at point p at infinite. Then accordingly, point P will be there, and if you draw a line from A to P, then it will be almost 90 degrees. So that's why we have taken alpha 1 as your 90 degree and alpha 2 equal to minus 90 degree. So just put the value of alpha 1 and alpha 2 in this equation. You will get E equal to 2 rho L 4 pi epsilon naught aero cap. That is rho L 2 pi epsilon naught rho aero cap. That is the electric field intensity if the line charge is of infinite length. This is the formula for electric field intensity if the line charge is of infinite length. That is equal to rho L 2 pi epsilon naught alpha rho aero cap. And this electric field intensity along the aero cap, that is perpendicular from the line surface. As you can say, this rho is along the point P, that is perpendicular from the z axis, or you can say perpendicular from the line charge, the perpendicular from the line charge. Let us say this will be a point. This may be point. If you take point P here, then this row will also be perpendicular from the line charge. So here you can see that this electric field intensity is in the direction of aero cap. That means this electric field intensity will act in the perpendicular from the line charges. Okay. In case 2, you can see that if point of interest is at perpendicular bisector of line charge. Perpendicular bisector of line charge means, let us say this point P lies in the midpoint from A to B. Let us say this AB have the length of 10 meter. So this point P lies at 5 meter, at a point of 5 meter, that is in between the point A to B. In that case, alpha 2 and alpha 1 will make an equal angle. Alpha 2 and alpha 1 will make an equal angle with the point P. So in that case, let us say alpha 1 is taken as a positive value and alpha taken as negative value. In that case, if you take, let us say, let me show you. Let us say this point P lies at this point. So from this point, if you draw a point B, that means you are making an angle of your alpha in the downward direction, and if you draw a point A to point P, you are making an angle in the your clockwise direction. So in that case, we have taken alpha 1 equal to positive term and alpha 2 in terms of negative value. So putting the value of alpha 1 and alpha 2, you will get the value of electric field intensity having this value, that is rho L upon 2 pi epsilon naught rho sin alpha aero cap. Okay, now in the third case, that is the last case related with your electric field intensity due to line charge, is if point of interest is at one end. Let us say this point of interest as is at one end. Let us say suppose this point P as at point P. So in let us say this point P as point B. Then in that case, the angle will alpha one will be 0 and alpha 2 will be minus 90 degrees. So accordingly, if you write the equation, you will get the formula for electric field intensity as E equal to rho L upon 4 pi epsilon naught aero cap minus AZ cap. Okay, so this is the electric field intensity due to line charges. This is the formula related or derivation related with electric field intensity due to line charge. All of you must go through the numerical, or you can do some numerical based on this electric field intensity due to line charge. Acha, let me show you some numerical from where, then take the screenshot and do some numerical. Wait. These are numericals from your unit 1. We have discussed this unit 1 in detail format, so I'm not going to give you. So use this numerical format. So we're going to discuss some electrostatic fields, that is electric field intensity due to line charge numericals. We will do that. Where is this one? So this is the electrostatic part. We were dealing about the Coulomb's law. We have seen the Coulomb's law. Then electric field density is already shown. Then there is the electric field, your electric field due to continuous charge distribution. We have seen. This is the formula that we have discussed. Now this is your line charge. Line charge derivation has been already completed. Now here you can see that a numerical is given. A surface charge. Let me show you surface charge is completed. Volume charge is there. Here is numerical. Okay. Hmm. This is the derivation part. We don't have any line charge derivation. So let us discuss some of the basic first. Your line charge is not line charge is derivation is completed. We will discuss in the next chapter. In the next topic is our your line surface charge density. The next topic is our surface charge density, that is related with this one. That means let us say you have a table and many charges are placed there. First we will complete this derivation part, then we will move to the numerical part. Okay, then only you will understand the basic concept regarding this surface charges or line charges or volume charge density. So let us say this is your table. The table have the three coordinate system, that is your z axis, this is your x axis, and this is your y axis. So this is your surface, and surface have only positive. We have not taken the negative charges. We have taken only positive charges placed along the surface of the surface along this surface. Now we have to calculate the electric field intensity due to this surface charge density at this point P. Okay, and this point P is a perpendicular is this point. Let us take this point P is on the z axis, whose coordinate is given as 0, 0, h, whose distance or the height of the point P from this surface is taken, and this surface is at the origin point. Okay, this surface having the distance or at a height of h is given. Now, accordingly, we will find the value of the electric field intensity due to this surface charge density at this point P. So it is theoretically it is written. Let us consider a uniformly charged distributed sheet placed in xy plane. So this is your xy plane. Okay, because the coordinate system values along the parallel along the xy plane, so it is named as the surface is placed along the xy plane, having surface charge rho s. This is the surface charge density given for this surface charge. That is your rho s is your surface charge density of this sheet. Okay. Now let us consider point P. We have considered point P having parameter or coordinate system 0, 0, h. That means it doesn't have any x or y axis parameter, and it have only coordinate in the z axis. That is, it lies on the z axis direction, z axis, where electric field intensity is to be determined. Okay, let us consider small area ds. Let us consider small area. This is your small area ds, and this is also small area ds, whose distance is at a, as this is the distance. We have calculated this distance as from the z axis. At this, when you extend this positive z axis in the negative direction, you will find that this small area named at the point A, ds, having the area ds is at a distance of rho. Okay, now let us consider small area ds at A. This is the place at this is the point at which the small area is taken. Now on the C2, whose distance from the origin is rho, whose distance from the origin is rho is taken. Now let the position vector point P from ds is r. Let the position vector point, let the position vector of point P from ds is r. That means position vector of this point P and this small area ds is r. As this is your as we have to calculate surface charge density in density, so we have concluded surface charge density. That means we have concluded small surface area, and accordingly if you find the integrate this small cross section area, we will get the surface charge density of this whole set. Similarly, in the previous topic we have discussed small line charge, so we had taken small length and we have integrated that small length, so that we had to find the value of total length, total charge along the line length. Okay, similar case occurs for this surface charge density. So this position vector is from point P to this small area ds. Now this r, when you go when you go to point P, you have to move from this surface area to point A. You have to move from A to O, then O to P. You cannot directly go through A to P. Just virtually we have taken this. Virtually, we have taken the position vector from point P to the small area ds. But when you move from A to P, you have to move from A to O, then O to P, O to P. As you can say, when you move from A to O, that means you are decreasing the length. That means you are decreasing the distance. That means you are moving in the opposite direction. In the direction, that means minus arrow will be there. As arrow is your positive direction, that means moving in the positive y-axis or positive x-axis or positive z-axis, you will make positive arrow. But when you move from in the backward direction, or you are decreasing the distance, that means minus arrow cap will be there, negative direction. That means the value of A to O will be rho minus rho arrow cap. Okay, when you move from O to P, that means O to P, that means you are in gaining the distance, that means you are increasing the length, that means you have to do the h into az, as the direction is in the z direction, so it is taken as your h az. So this is so accordingly the position vector r is, that is ap equal to ao plus op. AP equal to AO plus OP, and AO is given as rho minus arrow cap. Minus arrow cap is for your decreasing in the length or in the opposite direction movement. So here it is gaining the distance, so it is named as HAZ, and the final equation is written as minus a rho arrow cap plus HAZ as AZ cap. And finally, if you want to find the magnitude of position vector R, you will get under root rho square plus H square. So we will discuss, elaborate this surface charge density in the next class. Till now, all of you must go through the class. Okay, thank you.